Record button. Okay, welcome everyone to Map Time Davis. Today's workshop is called Is My Research Mappable? Intro to Mapping, to Map Making and GIS for Researchers. So my name is Michele Tobias. I am the Geospatial Data Specialist at the UC Davis Data Lab, which is housed inside the UC Davis Library. And just a quick intro to what we do at Data Lab. We are focused on data science and helping researchers with the entire pipeline of what they need for their data. So everything from data collection through workflow formulation to analysis to interpretation and visualization and things like that. So we like data and we like to do everything with data. And my job specifically is I'm focused on spatial data. So that is why I'm presenting today. So one of the things that we do at Data Lab is this workshop series called Map Time Davis. And today's workshop is very entry level. So don't stress if you are not familiar with spatial data at all. That is the goal of today, is to get you familiar with spatial data. But Map Time in general is it's a phenomenon that has happened all over the globe. It's a meetup for people who want to do things with spatial data and make maps. So Map Time is literally time for making maps. So I hope after today you feel comfortable coming to at least some of our workshops that are coming up. One in particular you might be interested in is on looking at the schedule here. So on November 16th, I will be presenting a workshop that is Introduction to Desktop GIS with Qgis. So if you're interested in learning how to use a desktop GIS, in particular, Qgis is open source. It runs on all major computing operating systems. So it's a good choice for getting started, and also it's just a good choice in general if you don't want to deal with licenses or if you work on something besides Windows. So hopefully you will be interested in joining us for that. And I will paste the link to our Map Time Davis schedule in the chat window in case you're interested in anything else we're doing this quarter. And we also have our videos there as well when we get those set up. So if there's a previous workshop that you'd like to watch and we have it videoed, then you can see it there. All right, let me just check my notes and make sure I've told you everything you need in terms of getting started. Yes, I think we are good to go. So again, feel free to use the chat window to communicate with me if you have questions, or I also don't mind if you have questions and you want to just say them verbally too. That's perfectly fine. All right, so I am going to share my screen and we will take a look at something besides little talking heads and boxes. All right. Thank you for your patience as I get all of these windows set up. Let me just do one more thing in my chat window where I can see it. Okay. One of the fun things about presenting on Zoom is that the Zoom controls are always in the way. So, all right. So again, today we are our workshop today is called Is My Research Mappable? Intro to Map Making in GIS for Researchers. And again, my name is Michele Tobias and I'm the Geospatial Data Specialist at UC Davis Data Lab. So today our plan is, this is a very introductory beginning workshop, and mostly we're going to be focused on concepts. We're not going to touch any software today, so don't stress about having to download stuff. We don't need that today. Some of our upcoming workshops, if you're interested, when you sign up, there'll be instructions for what software to download and have prepared. So today our plan is, let me get my focus right. The plan today is we're going to start with an intro to GIS concepts and what is spatial data. So we're going to look a little bit under the hood and understand what makes spatial data special, and what actually makes it spatial versus just, I call it regular data. So and then we'll take a look at some research examples just really quickly. Hopefully that'll give you some idea of how maybe your research can fit into a spatial component. And then also we'll talk about how to get started learning. GIS is a very large field. It's kind of analogous to statistics in terms of concepts and different methods and things like that you can do. So we'll talk about what kinds of learning options you have. And then finally, hopefully we should have plenty of time for discussion. So if you have questions or if you want to talk about research plans and things like that, we will have time for that. So that is today's plan. All right, so what is GIS? It's probably a good place to get started. So GIS is two things, and most people don't make the differentiation between these, but sometimes I find when I'm talking with folks, they get a little bit confused about what is this thing called GIS? So it's both a method of investigation and it's also a software system. So that's, I think, where some of the confusion sometimes comes in. So GIS can stand for Geographic Information Science. And no one will tell you what they, oh, I'm referring to Geographic Information Science today. They won't say that, they'll just say GIS. But when we're looking at that aspect of GIS, we are looking at asking questions about the spatial relationship between data. So where are things and why are they there? How do they interact with each other? What's driving the spatial relationship? So those are the kinds of questions we're asking. So in this case, Geographic Information Science is really the theoretical framework for understanding spatial relationships. So it's kind of like more of the research concept and the questions that we're asking. On the flip side of that, when we're talking about software, sometimes people refer to a geographic information system, and that often refers to the software itself, like the tools that we're using. So GIS in that aspect is a tool for making spatial data and also investigating the relationships between the data. So we've got the method of investigation, and then we have the tools that we use to do that method of investigation, and all of it is just called GIS. So that hopefully helps a little bit, but if I just made things a little bit more confusing, you can also just think of GIS as mapping in general. How we do it, both in terms of thinking about it and how we do it with software. All right. So GIS data itself is a little bit different perhaps than the typical kinds of data that maybe you've encountered before and maybe data you've worked with before. So what makes GIS data and geospatial data in general different is the location aspect. So I like to think of GIS data as being both location and information. Information being, I often think of it as kind of tabular. It's a table in my brain, even if it's other kinds of data. I like to think of it as a spreadsheet, honestly. But then also that tabular data has location information associated with it. So sometimes I also like to think of it as the where plus the what. So what am I interested in and where is that thing located? In terms of a more technical way of thinking about it, sometimes you'll hear people refer to the same kind of formula as the geometry plus the attribute information. So the geometry is the where, it's the location of the thing you're interested in, and the attribute information is information about that thing. So that's all a little abstract. So I have an example that hopefully will help. This is a screenshot from the Gas Buddy website. They also have a smartphone app. And the screenshot was taken back in 2017, I believe. So gas prices here are way lower than they are now. I actually went and checked the other day to see, make sure that it looks the same, and it does. So I figured we'll just use this and pine away for the days when gas was $2.50 a gallon. But anyway, the point of this is to show you that this is a real world example of GIS data or spatial data in action. So we have the what plus the where, or the geometry plus the attribute information. So I'm going to use my cursor and hopefully this shows up for you guys. For example, here I'm circling around this gas station at the corner of Lake and Covell in Davis. So this is a location, right? There is a gas station here. And the information we want to know about it is things like what is the price of the gasoline? So at this time when I took the screenshot, we have some attribute information here. So information about our location, and that is that gas here on this day costs $2.61 a gallon. So that's attribute information to go along with our location. We also have information, for example, this is the same station here, the Circle K at Lake and Covell. So we actually have an address, another piece of attribute information, including the city and then the type of station that it is. So this is a Circle K, for example. So again, we have location information that we can put on the map, but we also have this attribute information. So information about the location. So we have the what here and the where over here in the map. So again, this is why I think of spatial data as generally being tabular, because we have a table here and it relates to locations. So hopefully that helps a little bit to see an actual real world example, although be it from the past. So another important thing to think about, and I think this comes up a little bit more in my world because when we talk about things like metadata, the two places that I see this most is in the world of spatial data and then also in the world of library data. And since I'm a spatial person in a library, I feel compelled to mention this. So we have attribute data, right? We just talked about that. Attribute data is information about a specific location in our data set. But then there's also this concept of metadata. And metadata is actually information about the entire collection. So the entire data set. And it might be something like who collected the data? When did they collect it? So for example, in our Gas Buddy example on the previous slide, metadata about that particular data set is that it was collected in 2017. So that is information about the entire data set, not just one line of data in our data set. So I just want to bring this up. This is a little bit on the more detailed side, but just so you know, when I talk about attributes, I'm talking about individual records in the data set, and metadata is information about the entire data set. And metadata is important. You'll see it like if you go to download data, for example, like the USGS is really good about this. If you're downloading their data sets, oftentimes they'll come with a metadata file that tells you information about like when the data was produced, who produced it, what the license is, how you're allowed to use it, you know, any information about the attributes that apply to the entire data set. Like if there's any kind of like code, like a column that contains like some kind of code, like maybe land use codes, or if it's river data, for example, it might be like, you know, stream order or something like that. So it's a description about the whole data set. Right. So mostly, we're not going to talk too much more about metadata today. We're just going to focus on attribute data and location data. Okay, so now that we know what the main components of spatial data are, I just want to put it out there that I think just about everything is mappable. So you can see down at the corner, down in the bottom here, I have mentioned that, okay, most things are mappable. I'm sure there's something we can't map, but there are sometimes ways to figure out how to map things that are less obvious, let's just say. The key to this, the key to making something mappable is that we need a location. And locations can come in many forms. Probably the most familiar one on our list here is a GPS point. So something like latitude and longitude, that's very easily mappable, right? Like we can find that on a globe. We can put that into Google Maps and get that onto a map. But other things that are locations that maybe need a little bit of processing are things like addresses. So an address is, you know, to our human brains, because we understand how these things work, an address is a location, right? There's a way to find that on the globe, given a standard address. If we want to map it in a GIS system, we have to do a little bit of processing. Typically, the process is called geocoding, and that's possible to do in most cases. You could have something like a place name, like a city or a neighborhood name, for example, and we can find that on a map. Again, it takes a little bit of processing to get it into the GIS and have the computer understand it, but those things are mappable. There are ways to locate those on the world. And also things like counties. So anything you can think of in terms of like, you know, city, state, county, country, those are all mappable in some way, shape, or form. So we just need a location in order to take our attribute information and be able to put it onto a map. And I'm going to show you some, probably a lot more examples of this as we go forward. So I've lost my ability to advance slides. There we go. So everything is mappable, including things that don't exist. So this is sort of my extreme proof that there are ways to map pretty much everything. And so I'm going to give you some examples right now of mapping fictional entities, also because this is more fun and lighthearted than some of the other things that we can talk about in terms of mapping. So this slide is an example. This is a screenshot from a project called Placing Literature that unfortunately has lost funding and is no longer online. And I have been trying to find a better slide to put in here, but I haven't found anything that comes close to how cool this project was. So I'm gonna tell you about it, and we can hope that they get funding and put this back online. So what this is they have an online map, or they had an online map very similar to, you know, Google Maps. And the place markers that you can see, like I've circled this one in red here on Pine Street in San Francisco. What they've done is taken locations that are real world locations that happen in works of fiction and place them on the map. So for example, the one that I've circled here is a location that was in the book, The Joy Luck Club. So this is a work, generally a work of fiction, but because actual place names are mentioned in the book, we can actually put them on a map. So what happened here isn't necessarily something that really happened, but it's a real world location, so we can map it. And you can see, because this is San Francisco, there's a lot of markers on here. All these little kind of peachy colored markers are other places from other works of fiction that happen somewhere in this area. So when this map is working, when you zoom out, you can see, like, obviously some places are more popular, like New York City has tons of markers, San Francisco, tons of markers, other places not so much. But again, the point here is we have location information and then we have attribute information. In this case, the attributes just happen to be fictional things that happen, but they have real world locations, so we can put it on a map. This map is really hard to see on a PowerPoint presentation in a Zoom window. However, I'm just going to show it to you and describe what it is, and I can get you the links to actually see this. So this is a published map, and what this is, the map is entitled Mythical Creatures in Europe. The authors went through many works describing the location of mythical creatures, and that's what all of this little text is on the side, this teeny tiny text. These are actual citations that go along with the markers that are on these maps. So like, for example, this one's pretty big. You can probably see, oh, or this one's really good. So we've got some kind of sea monster here. And this sea monster was mentioned in some publication at some point. And so the authors were able to say, okay, we have a sea monster, that's attribute information, and its location is in this place in the ocean. I'm sure there was some general description of it. And so then they can place that sea monster marker in the middle of the ocean where it belongs. So again, we have location information and attribute information. And our attributes in this case are what kind of sea monster it is, and then probably also the citation for the work that described where the sea monster lives. But again, location and attribute information, that's all it comes down to. So we have these mythical creatures that presumably never existed, but we have somebody saying, in this spot, there are sea monsters, over here, there are fairies, over here, there are goblins, and we can put that on a map. And you can see down here also, this map has a really amazing legend for the artwork on here, which is why I like showing it, because it is very nice to look at. The art on this is very well done, but also it is actual research that happened into the body of literature in this particular area of interest, and you're able to make a map with it, because again, you have locations and you have attributes, but you can also do art with this. And then finally, my last example here of mapping fictional places is, this is a hand-drawn map from Tolkien of his fictional worlds, where he has drawn out on graph paper where these things exist. And Interestingly, also, we actually have topo lines. So these are lines that indicate elevation. So we could actually take this if we knew what each of these contour lines represented, like how many feet. We can actually map this, and we could actually make a digital elevation model of these fictional worlds. And we could do measurements if we knew, for example, like how big a square was on the graph paper, like how many, if that's feet or miles or something like that. We could actually put this into a GIS, and we could overlay other information on top of it. Probably not real world information because we don't have a real world location, but we could do mathematical measurements on this, and we could actually build a 3D model and walk around in it and stuff like that. So this is fictional data, but because we have that location information and then attribute information, if we'd have to do some digging perhaps, but we could actually put this on a map and into a digital map and play with it that way and do some spatial analysis on it. So again, these 3 examples are just to prove to you that all we need is location information and attribute information, and we can make a map. It can be a fictional map. It could even be a map that exists in some other realm. But as long as we have some form of spatial information and then attribute information, we have a map that's ready to go. Okay, so as you may have guessed, the point of this is not just to make maps, right? We have spatial data, and maybe we want to do something besides make a map. We have questions that we want to answer. And so that's where this term spatial analysis comes in. So spatial analysis is performing operations on coordinates and attribute data, often to answer a question. So we don't just want to make a map because, well, maybe we do, but sometimes we actually have questions that we want to answer about the spatial relationships. And we talked about that a little bit earlier in the talk about what is GIS. So one of our goals oftentimes is to answer questions about where things are and why they're there. So for example, I really like this example, but it's a major bummer because it's John Snow's cholera map from 1854. So that's why I like to start with the lighthearted examples, because some of the other examples I have are less than lighthearted. It's a little heavy. But you've probably seen this map, especially given the COVID situation. I think I've been seeing John Snow and his colleagues' map come up quite a bit as an example of mapping with epidemiology. So this slide is obviously, I made this presentation originally many, many years ago, but I've left this slide in because I think it's a really good example of spatial analysis. So if you're unfamiliar with this story, what happened was in the 1850s, there was a cholera outbreak in London, and John Snow gets credit for this, but there's quite a few other people involved in this particular line of research. And, as the popular story goes, back then, people thought that disease was spread by bad smells, this concept of miasma, which was close. Some things are obviously spread through the air, but in this case, cholera was not spread through the air, and they were trying to figure out what was going on. And so they took a map of London and they started plotting out where the deaths were. So for example, each of these lines, the lines are at a address. So you can think of this as like, this is Broad Street, for example. And each of these lines happens at an address location. So I kind of think of these as being like, kind of located at like the front door of the house that's on the block. So the roads are here, and then the blocks, the buildings themselves are kind of in this area on this particular block face. So each of these lines here represents, like this is a little bit easier to see with the scan. Each of these lines that go across represent one person that died at this address. And then also, in addition to the streets and then the number of people who've died at each location, they also have marked where the pumps are. And if you're familiar with the story, you're like, yeah, okay, pumps. We know where this is going. But the hypothesis was that cholera was spread through the water. And so people are getting their water from all of these water pumps around town. And so the question was, okay, so how are these distributed? We might expect that people who are dying will be closer to a particular pump if it's coming from one location. So we can take this map, actually, someone has scanned this map, we're taking a picture of it, and it's been able to be georeferenced. So that is a process of assigning real world locations to a scanned image of a map. And because London hasn't changed that much since the 1850s, there are enough street intersections that we can actually assign real world locations to some of the intersections and put this map actually in the real world. So if I turn on, you know, Google Maps behind this layer, it will actually line up pretty well. This is a static image, so we won't do that, but I do have the file ready to go if we want to play with it later. So what I've done for this analysis is someone digitized all of the death locations on this map. So that's what these orange and yellow circles are. And I've color coded them for the number of deaths. But in general, if you look at the spatial pattern of the points, you can see they're kind of clustered in one general location. And they're also clustered in general around one pump. The polygons, the blue lines that I have here, for example, these ones that I'm circling around, this is a process called a Voronoi polygon. And you can think of this as anything that's inside this polygon is closest to this pump. Same thing, like if we move over to this polygon over here on the left or the west side of the map, everything that's inside this polygon is closest to this pump. So you can see that generally most of the deaths are happening inside this polygon, or at least fairly near this particular polygon. And so you might ask, like, okay, you know, why are these people dying over here when this is their nearest pump? It turns out people were traveling to this pump and getting the water there for various reasons. But in general, you can see that it's not all the pumps that are causing the problem. It's like these ones on the outskirts of where the concentration of infections are. There are barely any in their polygons. In some cases, there aren't any at all. Also, the Voronoi polygons don't take into account travel distance. So this is just as the crow flies, as they say, so Euclidean distance. So it may be easier, for example, if you live here, it may be easier to get to this pump than that pump. So anyway, we could go on forever and ever and think of all kinds of things to investigate. But this example is just to show that sometimes we have maps and we have map data, and our goal is to really do analysis on it rather than actually make a map. The map can be nice to help people understand what we investigated and what we found out, but in this case, the real meat of what we're trying to do here is answer a question, which is, you know, are the pumps involved? What is the spatial relationship between the deaths and the pumps? So I think this is an interesting example, however sad it might be. But I like to use it just because I think it's nice and concrete. We can understand things like streets and pumps. These are things that, you know, we can intuitively understand. All right. So before we stop, we'll have a break for questions, I think, on the next slide. But one thing I want to bring up before we do that is the concept of good data versus bad data. So not all data is good. A lot of times we can go find data on the internet, but we need to understand things about it before we can decide we want to use it. So a lot of data does exist, but we want to be careful of things like, are there errors in the data set? For example, in the John Snow data, this morning I realized the data set I had didn't have these pumps digitized up here, and that made the polygons not do what they were supposed to do because it was missing information. So I had to fix that and rerun the analysis really quick and make a better slide. So not all data is ready to go. Sometimes there are errors, there are inconsistencies, and maybe there is missing data, like in the pump data that I was working with this morning. And that can make a data set unusable. It might be, for example, like the data I was just using, it just needs to be fixed. That was like, took me 2 minutes to fix and rerun the analysis. So not a big deal, but if I want it to be usable for my question, I need to fix it. Or maybe I need to find a different source of the data that is more consistent if I can't fix it. Or maybe I need to collect new data if the data that is out there isn't good. So not all data is usable in its current form. So things like addresses, while we as humans understand that that's a location, we need to process that before we can put that into a GIS program and put it with other data and overlay things together. Same thing with like census tract numbers. Yes, a census tract is a location. It is a place you can go there, but as a number itself, it needs to be joined up with other information in order to make it actually spatial and actually mappable. So that's something you want to think about as you're thinking about your research and putting data onto a map is how much processing does that data need? How much time will it take to do it? Is it feasible? So for example, if you have addresses, I hate to tell you this, not all addresses will geocode well. There will be errors and things like that. So it will take time to get them, into the right format and assess how well your process worked to get that data into a spatial format. It's not impossible, but it does take time. So you want to account for that, and you want to think about like, what is the process you're going to need to go through in order to get that data onto the map. Oh, I lied. There's a couple more slides. One thing I like to mention when we're talking about GIS is that GIS is not just one software. A lot of times we'll get emails from people that say, oh, I want to do this in GIS, and they are talking about one specific software, but GIS is this huge group of software and concepts and things like that. So there are a lot of different softwares out there, and we'll talk a little bit more about what to use in what situation in a little bit in a couple slides, but just want to bring this up that GIS is not just the one proprietary software that a lot of people are familiar with. There are both proprietary and open source options. And this slide is only a few of the things that are available to you. And if you need help figuring out what to use, let me know. That's one of the things I'm definitely happy and prepared to talk to you about, is figuring out what software is the best for what you want to do and your goals. And then the other thing is that GIS is everywhere in your life, whether you maybe realize it or not. You already are using GIS. So one of the ones that's been around forever, it seems, is weather forecasting. When you turn on the news in the morning to find out what the weather is going to be like, that's GIS. Your weather person is using a GIS to understand what the weather will be like, what the forecast is, what the models are showing for how, for example, like today it's super windy, like how long is the wind going to keep blowing? When is it going to stop? Where is it actually going to be windy and how bad is it going to be? That's all GIS. Specific weather models, yes, but it's under the hood, it's all GIS. Things like Google Maps, okay, you've used that probably before. Turn-by-turn directions, that's GIS. Your PG&E power outage reporting tool goes along with the wind today. Hopefully our power stays on. But that is also driven by GIS underneath the app that you're using. So you're telling them at your address you are without power or your neighbor's without power. And that is actually geocoding under the hood and assigning a location and reporting that back to PG&E so they can figure out what equipment might be affected. Also apps like eBird, Yelp, Uber, and Lyft, those all use GIS underneath the app itself to help locate stuff. And you can watch the car drive around. It's a map, so that's also GIS. And then something you may be less familiar with is that when you go on the internet and there are ads, your web browser sometimes is able to figure out where you're located based on your IP address. And it will decide what kind of ad to show you. So for example, if I'm a mayonnaise company and I have two different brand names, same product, but Hellman's, for example, is an East Coast brand, Best Foods is West Coast. I'm going to want to know where you're located so I know which version of the ad to show you. Am I showing you the West Coast one that you recognize, or am I showing you the East Coast one accidentally making you think there's a whole new kind of mayonnaise out there? This is also common. There's a couple of brands that I can think of, like there's an ice cream brand, for example, that has a similar situation. So if you don't like mayonnaise, think ice cream. But anyway, the point here is that GIS is really a part of everything that you're doing. So if you think about it, those are some other good examples of things that are happening in your everyday life that are using this spatial data, which again, I'm going to drive home, is location information plus attribute information, or the where plus the what. All right, take home messages before we get into questions. So we'll pause for questions and then we'll do some more like research examples and things like that, and then pause for more questions. So take home messages is that GIS is both a method and a tool. So the method about thinking about space and questioning where things are and why, and then the tool that we actually use. So it's got the same name generally, but I think that can can add to some of the confusion. But GIS data, I think you can probably say it with me now, is location information plus attribute information, or the where plus the what. We've seen tons of examples of that in this talk so far. Also, a quick reminder that attribute information and metadata are related, but not the same thing. Attribute information being information about your location, and metadata being information about the entire data set, who made it, you know, what year it was made, things like that. And that anything with a location is mappable. Sometimes even if the thing that we're mapping is fictional, or even the location is fictional, sometimes we can put that on a map. Hence, almost everything is mappable. But also everything is not just about maps, it's also about spatial analysis. We may want to ask questions about where things are, why they're there, and how they're related to each other. Okay, I am now unmuted. Sorry, we're having a little technical difficulty. Somehow I managed to get muted, and I think it was an accident, but Naomi, let me know if I was causing feedback or something. Okay, I think we're good. So again, it's not all about maps. Sometimes we ask questions about analysis. We want to know why things are where they are and how they're related. And then all data isn't created equal. Sometimes it needs processing, or sometimes there's mistakes, and we need to know that before we can get going with the data itself. So we may find, you know, data that we think is usable, but we should still vet it. We should make sure it is what we think it is before we just dive in. And then also examples of GIS are everywhere. There you go. Okay, so what I want to do right now is pause for questions. You are welcome to either unmute and ask your question, or you can type it in the chat, and I'll give you a 30 seconds or so to type in the chat if you're typing, because I know that takes a little while to do. But again, next up, what we're going to do after we field any questions is we are going to look at some research examples, like real world research, and then look at how to get started. So if you have any questions about the things that we just talked about, now is a good time to ask, or we can talk at the end too. All right, so I see Casper has raised their hand. Do you want to unmute and ask your question, or do you want to type it in the chat?
How are you doing, Michelle?
Hi.
I wanted to find out what causes a GIS supplied information tool like Google Maps, for example, to provide wrong information. Like where I come from in my country, you use Google Maps, you might be misled, it will lead you to somewhere totally different. So is it the network connectivity, or is it the information that was fed into the system?
I would think that it's more likely the information that Google has that's wrong. So what can happen is the data that they're generating is from a source that's either incorrect or it's old and hasn't been updated. But there are other sources of spatial information like Google Maps. Like you might want to check out a data set called OpenStreetMap that's editable as kind of like a Wikipedia, where anyone can edit it, but it's also it's proof, like there's a team of people who volunteer to check things that people add to it. So you might want to take a look at OpenStreetMap instead and see if that is any better. There's no guarantees, but it's just a different way that the data gets made. So it might have different information. But that's a great question. It looks like we've got some in the chat as well. So the question says, I noticed R wasn't listed on the software, though software like Python and Java were. I'm wondering your suggestions for dealing with spatial data in R, or if we should avoid R for analysis. That's a great question. I did mention that slide doesn't have everything on it. I think that was a screen capture from someone else's talk. R is a great way to work with spatial data. In fact, next week at Maptime Davis, we're actually going to have a talk about using Shiny apps in R, but also we have the Davis R users group on campus too, and a lot of folks that go to that have a lot of experience working with spatial data in R as well. And we'll talk more about options for getting help, but R is great. Especially on our Davis campus, R is kind of the preferred programming method for research in a lot of fields. So it's definitely something you should try. And I'm happy to help with that. Like, come to drop-in hours, I'll talk about when that is and how to access them in later slides. But R is definitely a good way to work with it, as well as, things like Python and Java and JavaScript. Basically, it's whatever you're comfortable with in terms of programming, but there's ways to work with spatial data in all of that. So hopefully that answers your question. Are there any other questions before we move on to some research examples? Okay, so not seeing any hands raised or anyone typing in the chat. We will move on to the next slides. And we'll have more time for questions for sure. So if you think of anything, throw them in the chat or write them down and we'll address them as we go. All right, so some research examples. Some current research examples, I guess, things that were published not in the 1800s. So I wanted to show you an example of a paper that I had published earlier this year with a couple of colleagues that was looking at, the paper title is Route Logic of the Central Pacific Railroad from 1861 to 1869. So the data is from the 1860s, but the analysis happened in the last couple of years. And what we were doing was we were looking at how the Central Pacific Railroad changed over time from the planning stages through what actually was built. And so we looked at 3 points in time, and these were based on maps. So these are print maps that were created in the late 1800s. And we went through a process of digitizing them. So they were scanned. And then they went through a process called geocoding, where we assign real world locations to different points on the map itself and make them spatial. So we have this image that now can overlay on top of things like, for example, you can see a digital elevation model behind one of them and topo lines behind the other map on the screen. But we could also overlay these maps on like Google Maps data or OpenStreetMap data or all kinds of things, because now they're located in space. So we can layer all these things up. But what we were interested in is taking these, it was 4 sets of maps, but 3 points in time, overlaying them all on top of each other to understand how the route changed over time. And you can kind of see in this, this example here on the right, that the original 1861 plan for this railroad was that it was going to go through Lincoln instead of Sacramento. But obviously that changed. And this is a section of the Transcontinental Railroad that runs in California from Sacramento all the way up past Lake Tahoe to the state line with Nevada. So it was interesting to look at how it changed. And using these maps, we were able to actually stack up all of these points in time and then digitize lines that we could actually look at and understand, and try to figure out why the railroad went where it did. And then over here on the left, you can see kind of a zoomed in section of one of the maps. So it's looking at this map. It's I'm doing a bad job of locating it. So I think it's in here in this section, kind of near Truckee. But you can see that the actual plan, the original plan is this red line. It's really similar to what was actually built, but one of the intermediate maps actually had the route going in a very different location. So the paper talks about why we think things were changed and why they weren't in some places. But really the key here, the reason why I'm bringing this up is to show you that you can actually take historic maps and you can digitize them and put them into a GIS and get information from them, and then put it into a GIS program and understand some things about those maps in relation to other maps, but also in relation to current day information, like this digital elevation model that shows, what the topography is of the Sierras in this area to help understand where these lines went and maybe why. A lot of the things that we discovered was that, obviously when you're building a railroad, you have to work with the topography. You can't just go straight up over the tallest peak. You kind of have to wind your way around to the places that are better to put the railroad. But sometimes when you have choices, you might make different choices depending on the topography. which I think is not really a surprise. But anyway, that's just one example. Another example, kind of along the lines of the John Snow one, going with epidemiology, is this web map that my team at Data Lab put out in the last couple months. So our goal with this particular map was to understand the UC Davis potential worksite exposure data and put it on a map, because legally we're required to put it out as a table to show where potential worksite exposures were, and it's linked to building names. So you get a table. I think I have an example of this. Yeah. So if you go to the potential worksite exposure website as it is, you'll see something similar to this. This is a screenshot from last week. Obviously the data has been updated since then, but it's a table. So you're trying to understand, like, okay, Olson, Boehner, this is a vet med building, Wellman. And immediately my brain is like, wait, how close is Olson to Boehner? I don't remember. I really want to look at a campus map. So my team was like, we want to see this spatially. What is the spatial relationship? And also the spatial relationship over time. So we built a web map that takes this tabular data from the people who produce the worksite exposure data, and we put it into a web map. And down here at the bottom, there's a timeline slider where you can actually play through each day and see how the buildings change over time. What's interesting is the data that we have starts in mid-August. Right now, we're working on scraping older data to add more to it. But before students come to campus, the exposures are predictably lower. And then as people come to campus, it gets more intense. You get more exposures, but only for a certain point in time. And then it just kind of stays fairly level. And also, one of the things I've noticed about this data is that buildings don't have exposures repeatedly. So it'll be like 1 or 2 days and then they turn off. They don't stay lit up. So that's kind of good news. But we wanted to use a map to understand how the spatial relationship works. Is it all, just like in like early or mid-August, there was a lot of exposures over in the vet school. And I was like, is that going to like stay in that area and then expand, or is it going to stay in that area? And the answer is it stayed in that area and didn't really expand, and also didn't continue. So I think having the data on a map actually is, at least for my brain, obviously take it with a grain of salt because I make maps for a living, but for me it's easier to understand what the relationship is between this tabular data. And again, we can take this data and we can make it spatial because we have the building names. And building names, we understand it's kind of like an address on campus, right? Like if I tell you I work in Shields, you can find that because maybe you know where Shields Library is, or you can look it up on the campus map. But there's ways to find out where that location is. So we went through a process of matching up the building names that are in this tabular data on the website to the campus building database that has the building footprint. So these are polygons, but essentially you can think of them as latitude and longitude points for each corner of the building. We can match those up based on the worksite name, and then we can make this spatial because we have the building location, and then we have the attribute information from the table joined up with the location. So we can actually make a map with that COVID worksite exposure data. And I think it's actually more, for me, it's more useful. Hopefully for other folks, it's more useful as well, just to see that and understand how it changes over time, because I'm not really good at understanding this, the list of dates and the buildings together. It's just, that's too many factors for my brain. So I like it on the map and we can actually see it over time with a timeline slider. So those are 2 examples of situations where we've taken 2 different kinds of information. We've done some kind of processing to it to make it spatial, and then we've put it on a map to understand the spatial and temporal relationships between the data that we're looking at. So similar processes, using existing data, making it spatial, and then putting it on a map to understand the relationships. All right, so that were just some examples of some recently released research on my end in my world. But now you might be asking, hopefully you're excited to think about making spatial data, but how do you get started with this? And on our campus, that is sometimes not as easy as we would like. So in terms of learning options, we have kind of a gradient from structured formal learning options down to more casual learning. So if you're a student or interested in, like, maybe you can audit a class if you're, faculty or staff, and you're interested in a more formal learning environment, we have traditional courses on campus. I generally recommend people start with LDA 150. It's taught, I think, every quarter now, because there's so much interest in learning this particular kind of data and analysis. But it is very highly impacted. It's really popular. So if you're a student and you're interested, plan ahead in terms of your passes, because it will fill up quickly. If you're a graduate student, there's also Geography 200 CN in the geography program. I generally recommend folks have some other background learning before they take that class, because it moves very fast. But also American River College is another local 2-year college that has a really good reputation for their spatial data classes, GIS and things like that. So if you're interested in doing that outside of UC Davis, that is a really good option too. Online courses, you have things like Coursera and Lynda that have really good things, really good workshops and courses that you can take. There's also, less formal learning things like, obviously you're here at Maptime Davis. We have a whole, quarter of workshops coming up and a whole year of workshops that we'll be doing. And the Davis R users group as well is a really good place to get help with, specifically with R and spatial together. So if you're interested in learning to work with R, or if you already use R and you want to add in spatial data to what you're doing, the Davis R users group is a great place. There's also things like online tutorials, and I didn't change the slide. GIS drop-in hours. Data Lab now incorporates GIS drop-in hours, so you're welcome to come see me on Wednesdays from 1:30 to 3, and I can drop the link into the chat in a minute for that, so you can sign up for that if you're interested. I'm happy to talk to you about any of the things we've talked about today, and also software options. But also you can give it a try on your own. Some people just like to get the software and start trying it. That's also a very valid way to go. Personally, I kind of came through the more traditional course offerings, and then, supplementing with things like workshops and tutorials and things like that. But, there are free options out there, so you don't even have to pay for the software. You can get started for free and just give it a try. Zoom is not being helpful with the advancing of slides. So again, this is another slide about software and some of your options. Again, there's a ton of software out there, and if you have questions, I'm happy to discuss more about what is a good option for what you want to do. And again, my first one on the list is QGIS. We're going to have a workshop, like I mentioned, in November for an introduction to GIS with QGIS. So that's a good option if you're interested in getting started with the graphical tools. So if you like having windows where you click in boxes and fill things out versus programming, I think QGIS is a great option. Also, if you don't work on Windows, it works on Windows, but it also works on Mac and Linux. So it's a good option if you're interested in staying in whatever computing environment you're comfortable with. But also ArcGIS, we have free access to that as well because of a license agreement. It was paid for, I think, by College of Ag. So we do have access to that, but it is proprietary software. So when you leave the university, you won't have access to that. But also other options in terms of programming are things like R and Python. If you're interested in databases, things like PostGIS, there's other spatial databases like Spatial Light or remote sensing, like satellite imagery focused tools like ENVI are also an option too, and many, many others. There are so many tools out there. And again, I'm happy to help you, figure out based on what you want to do and what your goals are, what would be a good option to start with in terms of software or programming language. Yeah, So again, we have help resources available. So if you're not, on your own to do this, if you need help, there are ways to get help. I would recommend most people start with Data Lab drop-in hours. So you can come and chat with me on Wednesdays from 1:30 to 3. And again, I'll put the link in the chat window when I don't have full screen stuff going on. And then I can also do one-on-one consultation. So if you have a question that's much bigger than drop-in hours, I may direct you to, doing a one-on-one consultation, but I would start with drop-in hours. And again, we've got Map Time Davis workshops going on all this quarter, Tuesdays from 10 to noon. And I posted the link in the chat earlier for where our schedule is. And then we have also an email, a nice old school email list called the Geospatial email list that has been on campus for many, many years at this point. And the goal of that is to get folks on that list who work in the field of geospatial analysis in any way, shape, or form. And we do things like announce workshops there, but also people can ask questions. So if you get stuck on something, seeing weird behavior with your software, or you're having trouble understanding something, you can email the list. And there is quite a few people on there. I think we're somewhere around 500 folks on that email list. So it's a really good resource for getting information. And it's relatively quiet given the number of folks on it. People are really respectful, and I highly recommend getting on that email list if you're interested in continuing with spatial data. Okay, so that is what I have in terms of our presentation for today, concepts and things like that. What I'd like to do now is give you guys an opportunity to discuss. So what I'm going to do is I'm going to turn off the recording so that people can feel free to ask questions and not be recorded. And then we will have our discussion then. Let me go ahead and turn that off. Sorry, one second, stop recording.